Alright guys, we're back with another lecture here, this time on section 6.1. This will be predominantly definitions with a little bit of some algebraic proofs at the end. And we want to talk about what we mean whenever we start using the word linear as it refers to transformations. What we want to look at today are the concept of mappings, right? So if you can imagine, suppose you have some space, some other space. I'm going to call this one U. I'll call this one V. And if I set up some sort of well-defined instructions, right? So it's well-defined as it takes some value in my first space. I'll call it U1. And let's say the instructions send this value over here to V1, and maybe it takes U2 and it sends that over here to, let's say, V2, and every single point in this left-hand space here, it gets sent somewhere at exactly one place, right? This set of instructions, we'll call this T. We would then call T what's called a mapping, right? And the notation we would use for this is we would say T, we put a colon here, and we list the first space, an arrow, and then the second space, right? So this says T is a mapping, and it maps the things in U to things in V, okay? Now, we have some definitions for these things, obviously. The space that you are mapping from, so the original space, this is called your domain. I'm sure you guys probably anticipated that already. And this one, not range, although that's the first thing that people tend to think of. The space that you're mapping into is actually called your codomain. The distinction between this and range we'll talk about in the next video, but for right now we have a domain and a codomain. And there's lots of different ways that you can develop these mappings, right? I'll give you a few examples. I want to bring up two very specifically here. So let's take this one as an example. Suppose we have Suppose we have T, and T here is going to map M to R, okay? So that's the space of all 2x2 matrices that have real entries, and it's going to map this to R. And these are two very different spaces. They're both vector spaces, right? But they're two very different spaces. And I'm going to define it in the following way. I'm going to say, okay, take some matrix in M2R, I'm going to call that matrix A, and we're going to map A to the determinant of A. Okay, and we can play around with this, maybe plug some stuff in. Let's see where stuff goes. So where would T map, let's say, 0, 0, 0, 0. Well, the determinant of this matrix is 0, right? Yeah? So this matrix gets sent to 0. Again, it's a map. It goes someplace, right? So how about the identity matrix, right? So there's I2. Well, that gets mapped to 1. Because, again, the determinant here is 1. Okay? Now, it's important to note that when we're considering these things, we'd like to consider the relative sizes. Okay? We tend to classify the size of these spaces by what we call dimension. M2R, from one of our previous lectures, is 4-dimensional. Okay? R is only 1-dimensional. So if you can think about it as if there are far too many things in M2 to be mapped nicely as in 1-to-1 with R. I'm going to have to send some matrices from M2 to the same number. For example, not only does this matrix get mapped to 0, but so does this one. Right? Again, take a determinant of this matrix, 1, 1, 0, 0. You also get 0. And in point of fact, T is going to map infinitely many of these matrices to 0. It'll map infinitely many of them to 1, to 2, to 3, to 1/2 pi, etc. I mean, it's R. It's not the collection of the integers. But this is a map, right? It has an interesting effect. Okay, I want to take a very specific example to explore something here. Okay, let's take the transformation of. Well, let's add together these two matrices. Let's add together 1, 0, 1, 3, and let's say 1, 1, 1, 1. Okay, now, what do I get? Well, this would be the transformation of adding these two matrices together. I would get 2, 1, 2, 4, and this determinant is, well, 8 minus 2 gives me 6. Now, I want to compare that to something. I want to compare it to, let's say, the transformation of 1, 0, 1, 3 plus the transformation of 1, 1, 1, 1. And so really what I'm comparing here is, I'm wondering, is this transformation going to have the same effect whether I add the vectors together first, then apply the transformation, or if I take the transformation of each one individually and then add them afterwards, right? So in this case, I'm adding the vectors first, then doing the transformation. Here I'm doing the transformation first and then adding them afterwards. And if we look at this, this determinant is 3. Okay, that determinant is 3. This determinant is 0. So that gives me 3 plus 0, which is 3. Those aren't the same. Yeah? Those aren't the same. Now, we're going to be interested in some mappings for which this property does hold. Okay? And we'll look at an example of those in a second, but I want to cover one more example of why this is not a very nice mapping. It's used for some things, but it's not a very nice mapping. I want to say, let's take a look at the transformation of, let's say, 2 times 1, 0, 0, 1. Okay? Now when we multiply a scalar times a matrix, we know that the scalar gets multiplied by every entry. So this is just the transformation of 2, 0, 0, 2, and that determinant, because that's my mapping, it's just 4. And again, I would like to maybe explore something here. What if we take the scalar out? What if I, it's okay to think of it as factoring out. What if I factor out that scalar? Does it come out the same? Well, I don't know. Let's see. The transformation of 1, 0, 0, 1, that would be, well, 1, and 2 times 1 is 2. And again, so this property doesn't hold either. I'm not allowed to take scalars out of my transformation. Now, this particular transformation, these things don't hold, right? But I want to show you an example of one where they do hold. Okay, so again, we'll keep this transformation in mind. Let me just go ahead and call this one T1 because I want to leave it up here. Okay, let's look at another transformation. There we go. Okay, let's map. Let's make T, and T is going to map R2 to R. Okay, so T is going to map R2 to R. And the action here is that t will take xy. Again, you just plug in some vector from R as a 2-coordinate value here. We're going to map this to x plus y. Okay, whatever the number that comes out to. And again, sort of exploring it, we can say that t would map the point 1, 3 to the value 4. 1 plus 3 is 4. Okay, we come up with the same issue here where my domain is a little bit larger than my codomain. So things are going to get squished a little bit. For example, again, 1, 3 gets mapped to 4, but so does 0, 4. And so does the point -1, 5. And so does there infinitely many points are going to get mapped to 4, and of course every other value as well. But I want to take a look at something. Okay? So, for example, what would I get if I took, let's say, and this time I'm not going to use actual numbers. Okay? What would I get if I took, let's say, x1, y1 plus x2, y2. Now remember the example that I did first over here, right? This property, I'm curious to know whether or not if I apply the transformation to these things after I add them, would it be the same if I applied the transformation to them first and then added the results afterwards, right? Well, let's see. So this would be the transformation applied to the vector x1 plus x2, comma, y1 plus y2, which by the rules of my transformation, you just add those components. So this would be x1 plus y1, x1 plus x2, plus y1 plus y2, which, because our addition here is commutative, is x1 plus y1 plus x2 plus y2. But this, x1 plus y1, this is the transformation just being applied to the point x1, y1, and x2, y2, that's the transformation being applied to the point x2 and y2. Okay? So you notice in this particular case, again, this works as a proof that for this transformation, any two vectors, when you plug them in, the value of the transformation applied to the sum of those vectors is the exact same as the value of the sum of the transformations if you'd done it before. Okay? Well, what about the other property we looked at? The other property we looked at involves taking a scalar and multiplying it, right? So I had, let's say I take some number a times the point x, y, and I'd like to know if this is equivalent to, what if I just factor the a out and I apply the transformation first and then multiply the a in afterwards? Well, let's see. Okay, so this is, when you multiply a scalar times a vector, again, it distributes component-wise. So we've got ax comma ay. By my transformation, this is ax plus ay. Because the distributive property holds for real numbers, this is a times x plus y. So this is a times, well, x plus y, that's just the transformation of xy. And so the property holds here. And again, these two properties, they hold completely for this particular transformation, and they didn't hold here. And this is the distinction between being linear and being non-linear. Okay? This transformation here, because these two properties hold, this is a linear transformation. So this is what it means to be linear. Okay? It's a linear transformation. It's got two properties. Specifically, these are called the linear properties, or individually, we say that this means that it is additive, or this is additivity, right? So if your mapping is additive, and this one is scalar invariance. Okay, so scalar. So if your transformation is both additive and scalar invariant, then it is a linear transformation. And if one of these properties does not hold, then you are, so this one is nonlinear. Okay? Linear transformations have a bunch of very nice properties, and that's what we want to focus on in section 6.1, specifically on linear transformations, and the ability to take a transformation, look at it, and determine whether or not it's linear. Well, I say look at it, but there's some work involved. Specifically, what we want to do is, given a transformation and given the information about it, we want to be able to write out these algebraic proofs which demonstrate linearity. Now, I can actually save myself a little bit of work by doing both of these at the same time. Okay? So if you look in your book, it's one of the theorems given. I'm not going to prove it because it's somewhat trivial to do so. Okay? But we can equate this idea of additivity and scalar invariance in one statement by saying, let me get rid of this, by saying let T, which maps U to V, be a mapping between vector spaces then T is a linear transformation if T of C1U1 plus C2U2 is equal to C1 times T of U1 plus C2 times T of U2 for all U1 and U2 in my domain, and C1, well, I don't know what my list of scalars is. I'll just put and scalars C1 and C2. Okay, so this is really just demonstrating both additivity and scalar invariance at the same time. This is going to save us a step in these proofs. These algebraic proofs get a little bit long, and we don't want to have to write these things over and over and over and over again. So we'll sort of save ourselves a little bit of heartache by trying to tackle it at the same time. Okay, let's take an example here. So how about we do this one? Okay, so let's say I have, I've got T, it's mapping R2 into R4. And I'm going to define the action of T by saying T applied to X comma Y is 2x plus y, comma, 3x minus y, comma, negative 5x plus 3y, comma, negative 4y. Okay. So again, what is T doing? I'm plugging in a 2 component vector. I'm getting out a 4 component vector. Again, mapping R2 to R4. I'd like to demonstrate that this is in fact a linear transformation. How do I do that? Well, to do this, again, you're going to take 2 arbitrary vectors from your domain, that's R2, and 2 arbitrary scalars. In this case, our scalars are going to be real numbers. Okay, And we'd like to prove that statement, right? So let's go ahead and see if we can't get an effective algebraic proof here. Let's say, let's let x1, y1, and x2, y2 be members of R2, and C1 and C2, they're going to be real numbers, right? So these are just the things I'm going to use. And let's see what we can say. So we would like to show that the transformation of C1 x1 comma y1 plus C2 x2 comma y2. Now we'd like to show that this is equivalent to, of course, if you remember the statement that was on the board, C1 times the transformation of x1 y1 plus C2 times the transformation of x2 y2. But I don't want to write that. What I want is to create this string of equalities to where this is the first thing written and the last thing written is C1 times x1, y1, etc., etc. So that reflexive property where this is equal to this, and this is equal to my second line, and that's equal to my third line, that reflexive property, transitive property, will give me what I'm looking for. So how do I do that? Well, I'm literally just going to plug these things in, right? These proofs are always going to be done by just plugging things in and sort of rearranging them to where you need them, okay? So let's see how we're going to do this. First, I need to actually add these things together, right? So this is effectively the transformation of, well, my first component will be C1 x1 plus C2 x2, and my second component will be C1 y1 plus C2 y2. Okay, so what would this give me if I actually put this into my transformation? I'm going to start a little bit further to the left here because this is going to be a bit long. Okay, my first component is 2 times my first component plus my second, so that's 2 times C1 x1 plus C2 x2 plus C1 y1 plus C2 y2. Oh, sorry, that's first component only. Second component, 3 times C1 x1 plus C2 x2, again, 3 times the first component, minus the second component, y1 plus, I forgot my C's, C1 y1 plus C2 y2. Third component, negative 5 times C1 x1 plus C2 x2 plus 3 times C1 y1 plus C2 y2. Now you see why we want to shorten this and don't want to have to write it all out multiple times, right? Okay, comma, negative 4 times my second component, y, so that's C1 y1 plus C2 y2. Oh, okay. Now, you can probably tell we're about to distribute and rearrange all of these things, right? So if I distribute these terms and then regroup them, you'll notice that what I can get here is I can get 2C1 x1 plus C1 y1 plus 2C2 x2 plus C2 y2. Now before I do the rest of them, again, look at what I have. This is the structure of the first component here, right? Except it's the structure using exclusively the values from vector 1. Okay? Same structure, but using the values from vector 2. Again, I'm trying to set up this sort of concept of having these two things separated to where I've got 2 transformations, one for my first vector, one for my second. So I'll do the same thing over here. 3C1 x1 minus C1 y1 plus 3C2 x2 minus C2 y2 comma, same thing here. Okay, I'll get negative 5 c1 x1 plus 3 c1 y1, and then of course negative 5 c2 x2 plus 3 c2 y2, and then the last one, negative 4 c1 y1 plus negative 4 c2 y2. Okay, and so now I can split these things, right? Yeah, now I can split them, and we're almost home free, right? I can split them into, take these two, split them into two different first components, right? So my first vector I'll use as the first component. I'll just underline them. So my first vector here is going to have first component, second component, third component, and fourth component, right? And then my second vector will have the similar components, but we're going to use the ones with the 2 index instead. Okay, so I'll underline those in, I don't know, I need another color. I don't know, brown, I guess. I don't know, I picked up a brown marker. Okay, so this one will be my first component for my second vector, second component, third, and fourth, right? Sort of track where everything goes. Okay, here we go. So this is going to be 2 c1 x1 plus c1 y1, comma, 3 c1 x1 minus c1 y1, comma, negative 5 c1 x1 plus 3 c1 y1, and negative 4 c1 y1. Okay. All right. And the remaining components I'll stick into my second vector here, so plus, and then my second vector is going to be the exact same structure, right? So this will be c2 x2 plus c2 y2. Okay, comma, 3 c2 x2 minus c2 y2, comma, negative 5 c2 x2 plus 3 c2 y2, comma, negative 4 c2 y2. Ugh, okay. It's a lot. I know it's a lot of writing, but again, focus less on the writing and more on the fact that this is not incredibly complicated. Now again, I've got this nice structure here, yes? But I want you to notice something. Every single term has a C1 in it, doesn't it? And for this second vector, every single term has a C2 in it. And so if I'd like to continue this string of equalities, one of the things I can do is I can factor those out, right? Because again, scalar multiplication is distributive among R2 and R4. So let me go ahead and pull that out. So I get C1 times 2x1 plus y1, comma, 3x1 minus y1, comma, negative 5x1 plus 3y1, comma, negative 4y1. And I'll do the same thing for the second vector, only this time, of course, we're going to pull out C2, leaving me with 2x2 plus y2, comma, 3x2 minus y2, comma, negative 5x2 plus 3y2, comma, negative 4y2. Okay? And if we look at the structure of what we have left, okay? If we look at the structure of what we have left, this is exactly this formula applied to the vector x1, comma, y1. Okay? This is C1 times, that's the expression you get when you put x1, y1 into the transformation t. And similarly, this expression is exactly what you get whenever you apply this to the vector x2, y2. So again, I had to erase some of the middle inequalities, obviously, because I ran out of board space. But what we had was a very large string of equalities, but every one of these steps are equal, and so therefore, of course, the first step is equal to the last step. And with that, we've proven that this is, in fact, a linear transformation. Okay? These types of algebraic proofs are fairly common when operating with things like this. They're not difficult, but they do require a bit of, I don't know, I want to say patience, but what I really mean is acceptance that it's going to be tedious and you're going to have to write a lot of stuff. Overall, not too bad. Okay, so practice some of these. We need to cover a few more things, but 6.3 is really where it starts talking about the specific structures of these mappings, things like kernel and range and things like that. And I've decided to do an entire separate video on that. So I'll do another video on 6.3. But for now, of course, again, you have homework. Make sure you get this done. The practice is important, and I'll see you guys next time.